And thank you so much for the introduction. I hope everyone can hear me well. So I'm going to talk a little bit about my work here at the Robot Mechanics Lab at the Department of Mechanical Engineering. So here, the motivation behind this work is to help find contaminants in the soil. Large amounts of natural gas, petroleum hydrocarbons, heavy metals, and other potential toxic elements have been discharged into the soil over the past few decades as a result of unfettered industrial activity. These excessive soil contaminants pose a severe threat to human and animal health by entering the food chain and migrating into drinking water sources. There are about 3 million potential polluted sites in Europe, and in the United States, there are around 1,500 sites that are categorized as impacted sites. So it's a great urgency that we need to address these growing challenges in soil management and soil biodiversity loss. The process of finding contaminants in the soil is the first phase of a soil remediation project. So traditionally, this involves humans going out into this environment to test, sometimes using hazmat suits to collect soil samples, bring back the samples to the lab, and then analyze them there. And this whole process takes around maybe a couple of days to sometimes a few weeks. Using robots for this task can help speed up this process, make it safer for humans, and particularly if you can leverage new types of sensors that are being developed, we can also reduce the time by not taking them back to the lab and just figuring out in situ. It also reduces human errors associated with the process that can happen through manual data collection or cross-contamination. So some of the challenges to automate this process are that we need to build a robot system that can move over different types of uneven terrain. Oftentimes it can be arid, it can be vegetative areas. So it can be any kind of these environments. The robot should also be able to collect soil samples and analyze them in situ, hopefully to reduce the time and expert individuals needed to analyze the sample. And oftentimes, while figuring out where to sample, they also need to prepare the soil, the terrain over there. So in case of vegetation, they might need to remove some vegetation. They might need to dig in a little bit. The EPA suggests that you need to collect soil samples sometimes up until 6 inches from the ground, depending on the environment. So you need to have some kind of tools like a rake or an auger to kind of dig in or scrap off some of the topsoil. And then when you have these samples, you also need to be able to figure out, okay, I have taken, say, X number of samples. When I have to figure out the next sampling location, I can take into account what information I have about these samples to intelligently figure out what is the next sampling location. So what we essentially want to do is release a robot into an environment like this and autonomously generate a contaminant distribution of the unknown environment without a lot of expert advice required to do this. And this process, an overview of this autonomous soil monitoring process can look something like this. You get a search area where you want to figure out what the contaminants are. You find the next sampling location and you make the robot move to the sampling location. If that works, then you prepare the soil for accurate analysis. We might need some input from that depending on what kind of environment it is, because we might have to use a different kind of rake to remove some of the topsoil or have an auger to dig in. We then deploy a specific sensor that can be used for this. We log the data, and then we estimate the contaminant concentration and use some model of figuring out what is the next best sampling location. And then again, this whole process goes over and over. So we have successfully implemented and deployed such an end-to-end robot autonomous system that can do this. We built robot systems that can navigate autonomously certain types of uneven environment to collect soil samples using in situ sensors. The picture here shows Patrick, one of the robot platforms used in this project. The sensor used is called a portable X-ray fluorescence analyzer, which is a portable spectroscopy sensors. So this is often in labs, huge equipments where you have to take in samples. It takes some time to analyze what kind of sample it is. So we have a portable version of this. I'll talk more about it in the next slide. And it is attached to a 4 degree of freedom arm on the robot. We also developed an adaptive sampling algorithm that takes into account the information from the samples collected thus far by the robot and predict the next best sampling location. So I'm going to talk a little bit about each of these points in the next slides. We used a portable X-ray fluorescence analyzer because we wanted to figure out, there's so many different kinds of spectroscopy sensors that's been developed, but what this does is it can give us the concentration of all the elements in the sample that are heavier than chlorine in the periodic table. So it allows us to give, we can, for example, go to sites that can detect lead. We can also do simple experiments, which is what we did in some field experiments in Pittsburgh, is we don't want to put harmful substances in the soil when we're conducting tests. So we spray salt solution, like sodium chloride, so we're detecting for chlorine. So that's why we picked the sensor, and also these are very new classes of sensors. So how this works is this was designed for humans, especially experts who know about environmental engineering and how to detect contaminants in the soil. They go around, take this, it looks like a big handheld gun, and you put it down on the soil and you wait for about a minute to get sensor readings. So in terms of sensors for robots, each sensor reading is expensive in terms of duration and in terms of information gain. Duration because it takes 60 seconds to get information, and information gain because it is hyperlocal. Oftentimes you want to get the contaminant distribution of a large area, acres and acres of land. But this will give you whatever is there within the sample under the sensor, which is around 1 to 2 centimeter square area. So it also needs to maintain close contact with the sample. So anything more or any kind of dust or any other sample that comes in, it'll have error. This kind of sensor is super different from all the sensors we use in robotics. Because think of a camera or LiDARs. Within a fraction of a second, we get so much information and also so much spatial information. Whereas this doesn't do both of that. And there's a new class of sensors like this called in situ spectroscopy sensors. One other example is the laser-induced breakdown spectroscopy sensor. And what this can do is you can train it to detect compounds, which gives you another way of detecting different types of contaminants in the soil and water, or even nutrients in the soil. So what we realized is we need a new type of exploration or sampling algorithm for these new classes of sensors that are being developed in the last decade or so. So I'm going to talk a little bit about the adaptive sampling algorithm without going into a lot of details. Traditionally, samples are collected in a grid-like fashion where people are sent out, and if the area is quite large, a grid-like fashion might be hard, but so they would do random locations. And this requires a lot of expert intuition that comes from years of experience. Again, these are really bad in terms of how much area we have to cover and how many sites we can cover. So we developed a dynamic sampling method that uses Gaussian process regression. For people who are not familiar with the Gaussian process, it is a probability distribution over possible functions that can fit a set of points. On the right side, you can see a 1D example of such a Gaussian process. The observations are made as red dots, and the prediction for the function that's being predicted, which is as a solid line, the 95% confidence interval is shown in the purple. So essentially what happens is close to the observation close to the sample points, the confidence interval kind of shrinks. And everywhere far from it, it allows more possible functions that can be fitted. So how we would use it is every time we sample a specific location, we would have some idea of the concentration, and that decreases the uncertainty of the nearby area. And it helps us find a better approximation function for the whole area. So we can do it in an iterative way. So every time a new sample is processed, we can fit it into the same Gaussian model, and then we can use it to plan for the next sampling location. So usually the math behind it is that a Gaussian process is fully defined by a mean and a covariance function. It's very similar to how Gaussians are defined too. So the equation here shows an important part of the algorithm that decides the next best location for a sample based on a reward function. The reward function here is a linear combination of the mean, the covariance, and a distance function. So we talked about how can you think about adaptive sampling. So typically what that involves is exploration and exploitation. So the mean function essentially tells that there will be locations that have high rewards if there is a non-zero mean value. So essentially exploitation. covariance over here, the term tells us areas that have high covariance. So it can be used to find locations that have very little information we know about, so essentially exploration. And the weight between both of them is determined by the parameter beta, which changes over the number of samples. So let's say you're taking around 20 samples. At the beginning, the value of beta will be small, and as you get more and more information about how the contaminant spread is and how you fit the parameters for the Gaussian model, you can then start going into locations that you've not seen and exploit. And finally, a distance function that takes into account the places you've already sampled, so you want to kind of repel from those areas as you take new samples. So to develop this algorithm, and before we can build the whole robot system, we developed a simulation environment that can help us design and develop such an algorithm without using a physical robot. This involved creating a large data set of maps digitally. But then once we started doing that, we realized that we had to characterize these maps. So for example, maybe these algorithms only work for a specific kind of contaminant distribution. So here are two such map characterization metrics that we thought about. One is on the x-axis is the density, on the y-axis is heterogeneity. And these are generic terms. Some can be classified easily and some need to be classified by more than one metric. But the idea here is that you can see there are some maps that have high heterogeneity and high density. Some maps have low heterogeneity and high density. So this is just one example of how you can classify maps. And why this is important is when you send robots out to these very different types of environments and different types of contaminants, they might be in one of these quadrants, and you might have to develop different algorithms, different parameters for the algorithms, or say, well, maybe in this situation, grid is better. So after experiences from field visits and interactions with the environmental engineers, we also realized there were many different objectives for remediation. So there was a image that I showed before. Oftentimes we're thinking about, let's recreate the contaminant distribution. But oftentimes in a remediation project, you don't want to recreate it. You just want to find out areas that are above a specific threshold. So I don't care how much it is, but as long as it's above a specific threshold, I want to remove the soil from there or treat it. So the remediation objective then becomes finding contours of contaminant areas that are above a specific threshold. It could also be find the average concentration or find hotspots, or just find local areas that have the highest data point. So each of these remediation objectives again determines how we run the adaptive algorithm and the parameters associated with it. So on the map characterization part, we saw heterogeneity. It's hard to characterize heterogeneity. We can easily see it. So some of the things that we use are areal extent or density. Morn's index is a spatial autocorrelation method, which tells us how different features are different set of features that can be there in a map are together or sparsed out. And the number of hotspots, again, it's easy for us to visually see it, but sometimes an algorithm can find the exact hotspots at the same location, but the values of what the contaminant is might be different. So we developed another way of figuring out distances between hotspots that takes into account the locations of them and also how much concentration is. And then finally, performance analysis. I'll talk a little bit about Earth's most distance in a later slide. We can also have other performance statistical measures like mean bias error, max bias error, and again, distance between hotspots. So in terms of the robot system, this project was part of my lab before I joined. So the first prototype is shown here, Caesar 1. It was taken to field tests. Most of the time it was teleoperated. It lacked a lot of the typical sensors that autonomous robots have, but it gave us a lot of knowledge about what kind of system we need to develop. So the new platform, our Patrick, was made with off-the-shelf components. It has motors from Heavy, which is a local robotics company that using which we made the 4 degree of freedom arm. It helps lower the sensor, and also, for example, in the back we have a rototiller, but we also could lower an auger to dig in and stuff like that. And this is the platform that we typically use because it can support the full autonomy software architecture that we've developed. And then finally, Caesar 2 is the custom designed Heavy platform itself. So we worked with them, and they're part of the grant that our lab worked on. And so It showcases how a completely different robot system can work with the same open source full autonomy architecture, and even the sensor they use is slightly different. So it can still work with different sensors and different contaminants, because as long as these kinds of sensors give us this hyperlocal, expensive information and you want some exploration algorithm, this system will work. Uh, to develop an end-to-end autonomous soil sampling robot, we had to design a whole autonomy architecture that takes into account motion planning, which involves finding, once you know the sampling location, how to go there, and also correct your um, plans as you encounter errors. Then you needed localization. So some of the experiments we ran, most of the experiments we ran used GPS and sensors on the robot, because it's easier than having to use a LiDAR and dealing with issues with that. But we also have a version that works with a LiDAR. Then we had the autonomy manager that takes into account safety protocols, the state machine for high-level autonomy architecture. We also had a data recorder that helps us record all the data for debugging information, running simulations, and also recording the information for the output of this whole process, which is the contaminant concentrations, locations, and the distribution. We also developed a GUI that the intent behind this GUI is anybody can open this GUI without any expert knowledge, tell the points that you want to send the robot to, and obviously the robot should be able to go there. And once it's there, there are some limitations of how uneven the terrain can be. It goes there and it does the whole process autonomously. And then finally, we have something known as the PXRF handler. Here, the portable X-ray sensor has to maintain close contact. So we use certain torque sensing capabilities that we design in the robot to make sure it touches it, but doesn't break it, because this sensor, the robot is an accessory to the sensor. The sensor is around $30,000, and the robot is just around 15. And yeah, so that's just an idea. That's just giving you a glimpse of the whole software architecture that we had to develop to conduct these experiments. Because having an adaptive algorithm is great, but if it doesn't take into account all the issues that can happen with an end-to-end robot system, then it is a little different than what the real world situation would be. Finally, with all of that, I'll show you one field experiment. This is obviously fast forwarded about 4 times, but even then you can see how long. So the robot goes from one sensing location to the other, taking into account all of the things that I talked about earlier, and it still spends quite a bit of time sensing, and it's super local. So the whole process, this is just a snippet of it. We had much larger videos, but I'll talk about why it's not here right now later. Essentially, it does the whole process autonomously, and it took around half an hour for this whole process to do 16 sampling locations. And the results of this look something like this. So here, we have the ground truth, where you can think of this as the bird's eye view. Darker green regions show areas with higher concentrations, and lighter regions with lower concentration. And the ground truth is done by manually sampling everywhere with a higher density. The adaptive reconstructed version looks something like this in the center, and finally the grid fashion was something that we wanted to compare it with. And even visually, you can see that adaptive is better than the grid. And we wanted measures to say that, mathematically. So Earth's most distance is a measure of dissimilarity between 2 distributions. You can think of it as the amount of dirt that needs to be moved from a lower concentration distribution to a higher concentration distribution. So this way it takes into account not just the differences in the positions of the peaks, but also how much work is involved. So the adaptive, in this case, performed 3 times better than the grid. And this is like a very simple example that I'm showing, but there's so many other problems that we face. Like there are certain distributions, map distributions, where this does not work. So to know when something works and when something doesn't work, I feel is important, and is often not considered in like these end-to-end solutions. So that's what we're working on right now. I also want to quickly mention some of the ongoing projects that are closely related to the soil monitoring project. So from the autonomy architecture slide, you can see that developing such a system involves engineering and research into different aspects of the robotics and system design. So the first project here focuses on enhancing wheeled robot mobility. Focuses on robot mobility in vegetative areas. So oftentimes robots need to go into vegetative areas, but they're really bad. And the idea here is that you use a lot of segmentation algorithms to figure out where vegetation is, and you repel from it. But a lot of times you probably want to go into the vegetation to do certain work. Uh, so to do that, we need to take into account a slew of different sensors, like proprioceptive sensors. Maybe I can't see anything, but I'm able to drive in. So I use those information to kind of figure out how I can improve wheel mobility in vegetative areas. The second one is enhancing wheel robot mobility for climbing steps. Uh, so this is kind of anecdotal, and we searched around to see that no one actually has any proper information about this. If you've ever driven a car over a big bump or a robot over a big bump, you would notice that if you approach it at an angle, you can actually go above more than what it can climb when it's heading straight on. So we ran a lot of simulations. We did certain analytical designs and realized if we go at an angle of about 45 degrees, there's a lot of conservations here. You can almost climb twice the step height that it was intended to. So we're trying to figure out what affects this. There's the aspect ratio, obviously a lot to do with the control of each individual wheels, the friction, and all of the above. But this is what we're trying to figure out. We don't want them to climb large steps, staircases. But if we can enhance the ability of what they can climb, this would help us go into areas that were previously inaccessible for wheel robots. And then finally, there's a pilot study that we're doing. This is because of our collaboration with an environmental lab where they have this fancy hyperspectral microscopy. It gives us information of think of a normal RGB camera. So a hyperspectral camera gives information past the visible region, and there's a lot of important information in detecting and identifying plant species. And our idea is that we want to do this for invasive species. Again, the sensors for these to put on robots are around like $10,000 to $20,000. They're more noisy than the microscopy over here, but the idea is that we finally got access to it and we learn how to use the system, and collecting data is hard, but we're trying to see if under, perfect lighting conditions and no robots involved and humans controlling how to get the samples, can we find important signatures to detect or rather distinguish between two plant species? So the idea here is that once we can figure something out, can we then make it work on a robot with a sensor mounted on a robot, and then comes all of the problems of sending a robot into a forest. But the idea here is to figure out invasive species from co-occurring non-invasive species. Since a lot of the work that I talked about involves ecology and sustainability, I would like to present how my work at the Robomechanics Lab conforms with the UN Sustainable Development Goals. The Sustainable Development Goals, or SDGs, were adopted by the United Nations in 2015 as a universal call to protect the planet. Our research work conforms with 6 different Sustainable Development Goals out of the 17 proposed by the UN. And we're planning to expand some of the work based on the results that we get with the related projects. Before I end my talk, I would like to thank all of my collaborators who have worked on this project, as well as Carnegie Bosch Institute for funding my entire research at CMU. It's really rare to find fellowships that support international students. We mostly cannot apply to any of them, so I'm super grateful for CBI to support this research. I would also dedicate this presentation to our beloved robot, Patrick. I hope they get wings and don't have to encounter any stars in their afterlife, because there was an incident where we have 4 feet of black water, which other means sewage water, that filled the entire lab, and we lost all of our robots. And so it's kind of sad. We're trying to rebuild the entire robot, but Aaron is very... Obviously, he's he's being in a good mood for all of us, I guess. So he said, we converted the entire lab into money, so now we can do something more. So this is where we are at with things at our lab. And thank you for listening.
May Patrick rest in peace. Any questions for Vivek?
Oh. Yeah, and I don't know, sorry if I missed this part, but the assumptions that you have on, so you mentioned that you use Gaussian assumptions for the diffusion, right? So I'm curious, are there measurements which you can take at a higher level, say, say maybe visual measurements, right, of photos which you can take to build an initial model which can then be fine-tuned, or even using the characteristics of how the contaminant would interact with the soil, So use those knowledge to actually maybe improve model or reduce the number of samples that you have to take. So do you do that already, or is that something planned?
So this is the work that we're working on. So currently we have no preliminary knowledge. So we're starting with no knowledge and we're trying to figure it out. But that was part of a larger journal work that we are going to submit because it involves the robot system, it involves the adaptive algorithm, it involves everything that we learned so far. So now that we're trying to push that out, the second one can be more focused on things like that. So we do have like a preliminary stage where that can be expert knowledge to say, don't go into these areas, and you can mark in the GUI and how that'll be. Obstacles can be not just like, big stones that you can go across, but also could be like, there's a piece of metal there and that's not going to have the contaminant you're looking for. And also a preliminary stage where you can send a drone to get some information. Most of the spectroscopy sensors at that large level don't really work, but there are correlations to them. So for example, topsoil temperature can be associated with certain contaminant distribution properties. So we could definitely take that into account when we are tuning the Gaussian parameters, hyperparameters. So we're having a preliminary stage where we're trying to do that in our current simulation-focused paper that we're working on now.
Thanks for the talk. This may be stupid, or you may have mentioned that and I missed that. So, when you do this sampling around, right?
Yeah.
So, and this is a very expensive measurement that you're doing. So, I'm wondering, is there any way to equip these robots with sensors in the bottom part, so that when you go from A to B, in the meantime, you can gather some information with respect to the path, and maybe there are other regions that is worth considering?
No, that's a really good question. So we kind of use the same sensor on another robot, again dead, which is supposed to be on. So it has magnetic wheels and it goes on top of metal containers. So for ships and other kind of metal pipes. So one of the advantages of that is all these are machined, and so you can kind of put the sensor very close and almost drag it, not drag it exactly, but almost drag it. But these sensors are not designed for that. So there was some work involved in figuring out how to repurpose them for that. So the idea here is that we start the sensing. So it takes 60 seconds and it spits out X-rays at different frequencies. But we have no idea of when it's doing what. So we kind of, this was not the work that I did, but how they tried to figure that out was you have this line across which you get it, and then you only look for peaks of a specific concentration. So it might miss a lot of information, and definitely the noise levels in that is way higher because a lot of this is proprietary information that we really don't have access to in the sensor. But I think with this new class of spectroscopy sensors, there might be sensors that can be continuously on, and we can do that. And even with the amount of noise that we had, if we do that over just 4 sensing locations and take the average, we somehow, in certain situations, have a better estimate. So it'll definitely work. But in uneven environments, it's going to be super hard. Like, I don't have an image right now shown here, but one of the, like you can see like small stones here. And when you actually put the sensor, even when we rake it, even if a small stone is just between the sensor and the sample, that sample reading is really bad. And it's really hard for us to know, did it hit one little stone on one edge? And how do we know if the sample is good or not? So it's hard to make it work well in an uneven environment. Yeah.
Actually, a ridiculous question. Have they integrated this spectroscopy sensor with camera? That would solve the rock problem.
So it would. Like if you had a camera at the bottom part, it would definitely help. I think that's some of the things that are things we found are only after going to different environments. Like for example, here's an environment just with grass. So we didn't see a lot of rocks, so we could use a ray. So it really goes with the environment, and we were just thinking like, oh, here's another thing that we need to adapt to. So it's definitely something that we can engineer for that specific purpose, for sure. But I think at this point, we spend so much time going to field tests, we're like, okay, if this journal work gets accepted, we can convince them that we have this robot system, so we can focus more on the adaptive part, which we feel like we need to focus more on. And then we can come back to re-engineering some of the things that we don't have. But yes, that will definitely help some of the noise that comes with it.
Okay, let's thank the speaker again. pass the control back to Alessandro for some closing remarks.